Hello students, this is Mr. Allen, and today we're going to look at section 8.8, which is on power series. We got quite a few objectives today. We want to be able to understand what the definition for a power series is. We want to look at the radius and the interval of convergence for a power series, endpoint convergence of a power series, and to be able to differentiate and integrate a power series. An important function, e to the x, can be represented exactly by an infinite series called a power series. For example, the power series 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. This would be the power series for the function e to the x. For each real number x, it can be shown that the infinite series on the right converges to the number e to the x. So here's our formal definition. If x is a variable, then the infinite series of the form a sub 0 plus a sub 1 times x plus a sub 2 times x squared, etc. is called a power series. More generally, an infinite series of the form a sub 0 plus a sub 1 times x minus c plus a sub 2 times x minus c quantity squared, etc., is called a power series centered at c. So our first power series here is centered at 0. The following power series is centered at 0, and we can tell that by just looking at the x's. Whereas we can see that this power series is centered at -1, because x plus 1, if you were to solve that equation, if you were to write that as an equation as x plus 1 equals 0, you will find that the solution is x equals -1. So it's centered at -1. The following power series is centered at 1. So again, we just look at the x's. You got quantity x minus 1, quantity x plus or x minus 1 squared, etc. So this could be a question. I think it's an easy thing, but you just want to be able to identify where the center of a power series is. A power series in x can be viewed as a function of x, where the domain of f is the set of all x's for which the power series converges. Every power series converges at its center. Here's the proof. F of c is equal to the sum from 0 to infinity of a sub n, quantity c minus c to the n. Well, c minus c is 0. 0 to the n is going to be 0. So we've got a naught, and by the way, the first case here we have n equals 0. So that's going to give us 1. So it's just going to be a naught. In other words, every power series converges at C. So C always lies in the domain of F. Now, if we look at this theorem down here, or this figure 8.17, we can see the 3 different scenarios for a power series radius of convergence. The radius of convergence can be a single point, C. The radius of convergence can be an open interval that's some distance r from C, or it could be the entire real number line. Those are the 3 scenarios. That's for the radius of convergence. So theorem 820 gives us the following. For a power series centered at C, precisely one of the following is true. The series converges only at C. There exists a real number r such that the series converges absolutely for all x's that are less than c away from r, and diverges when we are at any x value that's further away than r. And then finally, the third potential scenario is when the radius of convergence is for all x. So let's look at an example here. It says find the radius of convergence. So what we're looking for is what values of x is this power series going to converge. First of all, you should note that it's centered at 0. And in this case, we can see that f of 0 is 1 by plugging in 0. For any fixed value of x such that x is greater than 0, we're going to let u of n equal n factorial x to the n. Now we are going to use, hopefully this looks familiar, we're going to do the limit as n goes to infinity of u sub n plus 1 over u sub n. We're now going to plug it in the u sub n plus 1 over the u sub n. In this case here, the x, there's a common factor of x that can be pulled out. All the other factors of x will pull away, and n here is positive, so we don't need the absolute value of that. And this goes to infinity. This limit is equal to infinity. Therefore, by the ratio test, we can conclude that this series diverges for any x greater than or equal to 0 and converges only at its center of 0. So let's make sure we get this straight. We know that all power series converge at their center. In this case, the center is 0. The radius of convergence here turns out to be nothing. So therefore, the radius of convergence is r equals 0. In other words, it only is valid at 0 itself, and its radius of convergence is 0. For a power series whose radius of convergence is a finite number r, Theorem 820 says nothing about the convergence at the endpoints. It just tells us that within that radius it converges. Each endpoint must be tested separately for convergence or divergence. So that gives us 6 following scenarios. If the radius is 0, like we just saw in the last example, then it only converges at C. If the radius of convergence is infinity, then it converges for all x's. Then we can have the following scenario. We can have an open interval of convergence. We could have a open and then a closed part for our interval of convergence. We could switch those around, or we could have both closed. So those are the 6 possible scenarios. Let's look at another example. It says finding the interval of convergence for this particular series. All right, so we're going to do that ratio test again. We're going to we're going to do the limit as n goes to infinity of u plus 1 over u, absolute value. We're going to go ahead and make that substitution. We're going to multiply by the reciprocal. Lots of things cancel. We notice that the absolute value of x pulls out. Everything else goes to 1. So we get the absolute value of x. So you might think, well, what the heck does that mean? This tells us that the radius of convergence is 1. Moreover, because the series is centered at 0, its convergence is the interval -1 to 1. So let's go back here again. So we're looking at this. We get the absolute value of x. So think about that. Absolute value of x, we need that to be a number that is less than or equal to 1. So it makes sense that the radius of convergence here is 1. Now we need to check the endpoints. So this interval, however, is not necessarily the interval of convergence. To determine that, we need to test each endpoint. So I'm basically saying the same thing. So let's go ahead and plug in 1. When we plug in 1, we get the harmonic series. That's clearly divergent, so that's not going to be part of our interval of convergence. However, when we plug in -1, we get the alternating harmonic series, which is convergent. We've already studied that by the alternating series test. So in this example, the interval of convergence is the interval -1, including -1, to 1, not including the 1. Graphically, it would look like this. So and let me make sure I say this. So if whatever this power series, whatever the function is that this power series represents, what I'm telling you is, by finding this interval of convergence, as long as the x is within that interval of convergence, then that particular power series will be valid for that function, for any value in that interval of convergence. Okay, theorem 8.21, properties of functions defined by power series. This is probably the one slide that obviously everything we've talked about is important, but this is something that I feel like students in the past, I haven't done a good enough job of emphasizing this. So here's what it's saying. It says if we've got this function that can be represented by a power series that's centered at C, and we know that its radius of convergence is R, the following is true. The derivative of the function is equal to, now look at the power series and how it's changed. N has changed from 0 to 1, and notice that we've used like the chain rule on that function. Look how that has impacted the expansion of this particular power series. Similarly, look at when we do the integral of the function f of x. Now we put a plus c in front of the power series, and now we're using our power rule for integration. Now notice here the n still stayed at 0. The radius of convergence of the series obtained by differentiating or integrating a power series is the same as the original. The interval of convergence, however, may not be, so you have to be careful with that. I would highlight that, particularly if you're someone shooting for a 4 or 5 on the AP exam. All right, so let's consider the following function. We've kind of already looked at this one. So we've got x to the n over n. We're going from 1 to infinity. We're summing these up. We're going to find the interval of convergence for each of the following. The integral of it, the function itself, and then its derivative. So by theorem 8.21, we have the following. So what we're doing is we're looking at part C here, okay? So if we do the derivative of our function here, we're going to get x to the n minus 1, which is 1, plus x squared, plus x to the third, etc. The integral of f of x is going to be c plus, and now we're going to do the integral from 1 to infinity, and we're doing our power rule, which gives us c plus x squared over 1 times 2 plus x cubed plus 2 over 3 plus x to the 4, etc. By the ratio test, we can show that each of these series has a radius of convergence of 1. Now let's look at the endpoints. We have a radius of convergence is 1, so let's look at the integral. So the integral, we have the series x to the n plus 1 over n times the quantity n plus 1. It converges whether we put in 1 or negative 1. So its interval of convergence is negative 1 to 1 inclusively. Now for the function itself. So we haven't done anything integration or differentiation wise. It converges for x equals negative 1, but it diverges when x is equal to positive 1, which again, we're talking about the alternating harmonic series and the harmonic series. So our interval of convergence here is inclusively at negative 1 and then excluding 1 itself. Then when we look at the derivative of our function, we get the same radius of convergence of 1. We find that in this case, it doesn't converge at either negative 1 or 1. Therefore, this thing has an open interval radius of an open interval of convergence. Still, the radius is 1. And that will wrap it up.